go through the brief introduction again. So you have seen the opening slide, and I am Shakhawat, and I also work in the Uppsala University in the Department of Pharmacy, and mostly working in the SMD simulations. So the content of my work is like, first I will go through some of the practical informations, and I will also talk about a bit of amino acids, which are mostly important for this talk, especially because I will talk about more of like peptides and peptide aggregation. And then the important steps in studying a typical MD simulations, and also go through some of the examples of aggregation simulation studies and how to perform the analysis on the aggregation simulation, and also talk about a bit of the coarse grain MD simulation and some of the examples of our research work. So some of my talk, part of my talk will be probably, I mean, Alexi has already explained a little bit, but I will go through them probably a bit of again. For example, the most available open source softwares which you can use to perform MD simulation. There are a bunch of them like GROMACS, NAMD, LAMPS, and other softwares available, but GROMACS, I think the most flexible one. There are some others very good softwares as well, like Charm and Amber, but they have academic version, which has quite a bit of less flexibility than the version if you buy them from themselves, I mean, from their company. But among the open source software, GROMACS is, I think, the most widely used. So to start off the simulations or perform the MD simulation, you basically need three different types of files. So first, you need the PDB file, which contains all the structure information of all the molecules you want to use in the simulation. And then we need the topology file, which contains all the information necessary to define the molecule and molecule-molecule interactions within the simulations. And the input parameter files defines how you want to perform the simulations, like what should be the pressure, temperature, the time steps, and how long you want to perform the simulations. So let's go a bit of details into these topics. So the PDB file first, the structure files. Here's an example of the structure file. So it contains all the atoms, it numbers all the atoms, and it numbers all the atoms, and it defines basically its coordinates. So it basically defines its X, Y, and Z location into the system. And for many proteins and other things, and one of the common place you can find these structure files is like this website called RCSB. And here is what it looks like. And here, I think in the search, if you can write the PDB ID for any molecule you are looking for, or you can write the name of the proteins, you can find it from here. And it will give you the PDB ID, which you can use directly into the simulations. If you use GROMACS, then what will happen is like then GROMACS will try to convert it into its own format, but that it can do it automatically. You don't have to do much. You can just probably write some commands and convert the PDB file into the .gro files. And here's an example of this crystal structure of like this recent SARS-CoV-2 main protease in complex with some inhibitor, although I removed the inhibitor. And when you download the PDB file and you try to visualize it some software, you can use different softwares like PyMol or VMD to visualize this, and you can see how it looks like the structure of this molecule. So most often you can get the PDB file, the proteins or some of the peptides, but some cases you will not be able to get the structure from here. For example, the drug molecules, some of the novel drug molecules, then you can actually draw them with using some other softwares. I can show some examples with PyMol later in my lecture. So then once you have the structure file, like the coordinates of all the molecules, then you need the topology file. And the topology file contains all the atom types are assigned to define different elements of the molecule, the charge state of each of the atoms in the molecules, and the mass of those atoms, and also the connectivity of those atoms, which includes the bonds, angles, and dihedrals and impropers. Some of these are explained already in the Alexis lectures, like the bonds, angles, dihedrals, and impropers. I'll just show you how they are defined in the system. So first, in the topology file, you have all these defined molecules or atom types. And these atom types are named for, can be from different residues like protein or amino acid residues. In this case, these are from amino acid residue alanine, and their charged are defined here, and also the mass. And then it also contains the connectivity, like the bonds. For example, in this case, these atoms are numbered 1, 2, 3, 4 to whatever number it is, and then you can see that these are connected, like 1, 2, and 1, 3. They are the bonds, and then they are also connection. Also the connectivity is defined for their angles and dihedrals. So some of these things can be pretty common to the people who are already using the MD simulations for different purposes or in their research. But the people who want to start the simulation can be very important for this kind of information. And then these topology files, the structure of these topology files can be a bit of different based on the different force fields, but in GROMACS, you can perform the simulations with the number of different force fields, like the AMBER, CHARM, GROMACS, and you can also download any of the newly developed version, like CHARM, new developed versions, and then you can keep it in the folder, and then you can also use them using the GROMACS. So these are briefly the topology file, but you can see only the connectivity, but how those parameters are defined. Before going into that, I can just quickly talk about a bit of these different amino acids, which I will be showing some of the examples in the peptides. So basically, there are 20 different amino acids which are used, natural amino acid, which can be used in the simulations directly. There are some non-natural amino acids as well, but to implement them, you will have to do some more work. But in all the force fields, what you can directly use these amino acids. Some of these amino acids are charged, like arginine, histidine, and lysine, and some are negatively charged, like these aspartic acids and glutamic acids. And then you have some which are more of has polars or uncharged side chains, and some are more hydrophobic in nature, like alanine, isoleucine, and tryptophan and tyrosine, and there are some special cases. So all these, as I said, all these amino acids are pretty much well studied with different force fields and well parameterized. So you can use directly those parameterized. And by the connection, if a bunch of amino acids are connected together, they can form these different types of proteins and peptides. So this parameterization of amino acids is supposed to be quite easy, right? They have only a bunch of molecules like carbon, hydrogen, nitrogen, oxygen, and sulfur. But the problem is their characteristics can be quite different. For example, the carbon can act as a polar carbon. It really depends on where it is located. It can also act as non-polar carbon. It can also be in one of the benzene or aromatic carbon rings. So for these 20 amino acid residues, all these different types of carbons and all these different types of molecules are pretty much well defined. For example, I will show you for one of the examples, like for AMBER force field. And here you can see that all these different types of carbons are defined. And if there are almost 12 different parameters for hydrogen itself. Hydrogen is one thing, it can be attached to nitrogen, and it can be part of the water molecule, and also it can be part of the aromatic carbon ring and different other places. And based on that, all these different parameters are defined for the Lennard-Jones potential. The Lennard-Jones equation is already showed by Alexi, and there you can see that there are some parameters you need to define the molecule. And for these different types of molecule, there are these different types of epsilon and sigma value which are defined. So, and for these 12 different hydrogen parameters or 2 different hydrogen molecule or hydrogen atoms, these parameters will be slightly different. So this is one thing, defining the Lennard-Jones potential for the non-bonded interaction. This will mainly take into action when two atoms from 2 different molecules will interact with each other. And then you also need to define the partial charges, and there are different force fields actually use these different partial charges. different methods to define the partial charges, and they can be slightly different. In Amber, they mainly used a method called like restrained electrostatic potential, or RESP method. And this is a very widely used method for assigning partial charges for various organic compounds. And this is mainly derived from the quantum calculation by using the Gaussian calculation by using the underlying quantum chemical methods. And this actually tried to intense the resulting overpolarization of the molecule to approximate the self-polarization that occurs in the condensed phase settings. In the CHARM, they used a similar but a bit different methods, and they also considered the interactions of the water molecule, like T3P water molecule present in the environment. So all these partial charges for these 20 different natural amino acids are pretty much well defined with different force fields. Now, one of the question was like, whichever force field you are using, that actually depends on what are the problems you are solving. And you really need to go through the literature very well to understand which force field was used for those particular problems, and then how close the results were to the actual validation work from those force field studies. So once you define the partial charges, here you can also see that alanine is like in one state and histidine in two different states. So for these two different states, the overall charge distribution on the different atoms can be slightly different. So once you define the partial charges, one of the other thing would be like to go through these angles and bonds. And the bonds are also defined. So for example, for this different molecule definition, like for this different carbon molecule and different hydrogen molecule, they have like different types. So their bonds will also have like different characteristics, probably slightly different characteristics. And those are defined in the bond and angles and also the dihedral and impropers. So these parameters are basically the stiffness of the springs or the restraint force. For example, in one of the Alexis slides, you can see he showed the two beads are connected with the springs and how stiff are those springs. So those are depends on the parameter values, and those are actually given in this topology file descriptions. Similarly, the dihedrals and impropers, how the angle can move compared to the overall molecule. So those are all can be defined, and the stiffness and the limit of the angle variations can be defined in these topology files. So as I said, this slightly different parameterization can be happen in different force field because they are derived from different angle of point of view. And then once you have the topology files, we only need the input parameter files, and input parameter file actually defines the integration scheme, like what type of integration you are using to solve the Newton's second law of motion, and then the method you are using to perform the contact search algorithm, and also what are the time step you are using in your simulation, and the reference temperature, pressure, and the desired output options. And here is some of the examples of all these definition, what you can use, like the integrator scheme, the time steps, and how many time steps you want to perform the simulations. And also there are like temperature, the reference temperature and reference pressure, and in addition to what type of pressure and temperature scheme you are using. So overall, the key steps in the MD simulation is like the prepare molecules, the PDB topology and input parameter files. And then when you start the simulation, you need to perform the energy minimization first, because when you enter or insert all the molecules in the simulation system, some of the molecules might overlap, some of the beads or atoms might overlap with each other. So that's what we don't need to have in the simulation, because that can lead to instability. So we need to, the molecules need to push each other, and then you need to come up in a energy equilibrate system. And then you need to equilibrate the system to a certain temperature and pressure, or your desired temperature and pressure. And finally, you need to perform the final simulations, where you can capture the overall dynamics of the system. And then when the simulation is done, one of the important part is often mistaken in MD simulation is to perform the analysis, and how novel analysis you can perform on your simulation results. That's one of the key in understanding the simulated system. So here I will show an example of like an aggregation of a sample peptide. Let's see, I have one of the message here, and yeah, okay. So here is like one of the like made up or sample peptide. So one of the thing I want to show you is like how I can make this peptide using PyMol. So let's see, I will just quickly show you. And not only these peptides, using PyMol, you can also make different molecules or therapeutic molecules or drug molecules you want. So the PyMol is basically, you can download it. I mean, PyMol is an open source software probably, and you can download it for all these different operating systems, and then you can use it to get the structure or the structure of the peptides or molecule you want to use. So first you can go here is the builder, and in the builder you can see there are like two different options, both the chemical and the proteins. And if you click protein, you can see there will be like different amino acids, and you can also draw based on the different chemical structures. So I will show a quick example of drawing the protein structure. And here you can select the protein. What we are using was like this sequence: alanine, proline, tyrosine, glycine, and valine. And you can just select this in serial like alanine, and then it will show you create as a new object, and you can do it. And then you can see that there's this circular here, which it will add the next protein to here. Like what was our next amino acid residue was proline, and then it added the proline, and then at the end of each structure it will add now the tyrosine, and then I will need glycine and valine, and we can add the glycine, and then we can just click valine. So the protein, the peptide we want to perform the simulation is now done, and then you can just go and save or export the molecule into your desired PDB format. So if you click save here, you'll see this PDB, and then you can just give it a name, and then you can save this protein or peptide. So that part is quite simple to get the structure file. Now I will go back to my presentation mode again. So once you have the structure file, I mean that PDB file, that means you have the structure file, and you can then visualize that using VMD or PyMol or some other software, and then you have the structure file now with these five different amino acids, and you can see they are like colored based on these names. And then we need the topology. And the topology, like if you use GROMACS, you can use for the known amino acid residues. You can make the topology pretty easily, and there are some commands you can follow, and then you can get the topology files. So once you have the topology files, to perform the simulation, now you need to define a simulation box. And in the simulation box, you need to enter the number of peptides or the peptide molecules at your desired concentration. And once you have inserted all the peptide molecules, then you need to add the water molecules or solvent the system. Then you need to add the ions if required to balance or to make the overall system neutral. And then you need to perform the energy minimization, equilibration, and production run. So here are the examples. Like here is a simulation box, which is defined as like a cubic simulation box with side length of 8 nanometer. And then I have inserted 12 molecules here, 12 peptide molecules here, which is equivalent to 40 millimolar of the peptide concentration. Now, one thing is pretty much important here, that the limitation of the simulation system size and time scales. So you can see here the simulation system box was only 8 nanometer. So I'm planning to perform an all-atom molecular simulation, and how much you can actually perform the simulation using all-atom simulation methods, and what is the biggest scale you can simulate. I mean, the biggest scale I simulated is like a cubic box with 15 nanometer side length, and it takes about 2 weeks using one GPU node to perform the simulation for like 500 nanoseconds. So clearly there is some limitations. If you go higher than 15 nanometer cubic box, it will take, I mean, let's say you want to perform a cubic box with side length of 50 nanometer, it will probably take months. And if you go higher, it will take probably years. So those are not realistic to perform the simulations. So there is the limitations of the concentration you can use. I mean, of course, you can use the concentration at any amount, but imagine like you want to study the aggregation behavior of a peptide with a concentration of 1 millimolar. Then within this 8 nanometer side length cubic box, you will have like less than 1 molecule. So you cannot really study the aggregation behavior. So all these things you need to consider before you plan to run your simulations. And as I said here, I am planning to running a simulation of these peptides for like, which is equivalent to 40 millimolar. And then that means like 12 molecule in the simulation box, which can give me roughly to understand the aggregation behavior of these peptides. So once we insert the molecules, we solve it to the box, like add the water molecules. And then we perform the energy minimization, because since we added so many molecules, water molecules and peptide molecules, there will be a bunch of overlaps. And then during this energy minimization process, the molecules will push each other, and then it will become like energetically balanced. And then you will perform the equilibration, where we normally make our desired temperature and pressure. So I can see, I mean, you can see that I want to perform the simulation like around 310 Kelvin. And then it initially rises the temperature and it kind of like oscillates close to 310. And then I also want to perform or equilibrate the system at 1 bar. So initially there was like huge oscillations, and then it closes or equilibrates to 1 bar. So all these things I described, like the insertion of molecules, solvating the system, adding the ions and equilibration, I mean, they are like kind of very well described in different examples in these tutorials. I mean, if you really want to start your MD simulations, you can really start looking into these tutorials. So all the GROMACS commands and even the input parameter files, they are all given here, and how you can generate the topologies for like the known amino acid residues and all those things. You can probably really be helpful. I mean, you can really get helpful information or the command information from these examples. They have like different examples, but this first one would be like very generic to start a typical MD simulation. And then you have also performing, you can also go through the other examples to see how they perform the free energy simulations or free energy of solvation simulations. So here is like my simulations, and you can see here that when the simulation is done after the final production, all the molecules are now kind of like aggregated into one. And then when they become aggregated into one, then they kind of like, some of the molecules also like detached from the main aggregate or from the large aggregate, and then they become free monomer again. And here you can see that this is a one aggregate, but this is like broken into two periodic boundary conditions. So this is part of the same aggregate, but this actually goes across the periodic boundary condition. So this is what I am saying, like finally you can get the simulations from the MD simulations, the whole trajectory, but then you need to understand this, to understand the simulation, what you have observed, you need to really perform the analysis of the simulation trajectory. And to perform the analysis, Alexi has already showed a bunch of options which you can directly use from GROMACS. But instead of that, in addition to those, you can also use your Python coding. You can use different help softwares like MD analysis and use them into your Python coding to perform more sophisticated analysis of these trajectories. Like we can, once this simulation is done, we can then perform how many of the molecules were in the aggregates during the trajectories. Like here in this case, we consider the molecules in aggregate. If two molecules are in close to each other, within 0.5 nanometer distance, then you consider them as an aggregate. And you can see that initially the molecules are mostly monomers, dimers, or some other aggregates. But then with time, after 100 and 200 nanoseconds, they become like a 12 mer, like all the 12 molecules were in one aggregate. And then some of the molecules getting detaching from that large aggregate again. So this overall state of the molecules, whether they are in aggregate or not, you can get from this coding and from the trajectories. And then you can also plot the overall aggregate size distribution, like in these 500 nanosecond simulations that we have done, how many times we could see a 12 mers, or how many times we could see a monomers or dimers or trimers or tetramers in the other aggregate sizes. I didn't plot here the monomers because it will become very much higher. So these are very important information to understand whether a peptide molecule is like more aggregate prone or it is not aggregate prone. For example, since they are like the 12 molecule aggregate size is the most frequent here, so it suggests that this peptide, what we have made up here with these 5 amino acid residues, is like quite aggregation prone. And then we can find out our more detailed analysis, like how they kind of like this aggregation pathways evolve, like what are the what are the aggregate sizes can form from a monomer. Like a monomer can initially go into a dimer, like if you see these arrows here. So this overall aggregation pathway image here, these are like different aggregate size. And the size of these boxes shows how frequently they are in the simulation box. And the arrows shows like when this one aggregate states, it becomes or it goes into the other aggregation states. And the thickness of these arrows actually represents like how many times this type of state conversion or state travel occurs. Like for 1 to 2, it happens. And then we can see that mostly 11, when it becomes 11, a bunch of 11 can becomes 12. And the molecules can also detach from the 12 mers. So it can also become 11. So all this aggregation state transition, we can see from these aggregation transition pathways. Then we can also try to understand like how this aggregation proceeds or what actually drives this aggregation process for these peptides. For example, this residue contact map. And we can see the tyrosine residue, which when I describe the amino acid residue is like one of the hydrophobic residue. They have the most contact with each other, like with each other, with each peptide molecules. And we can see that this middle peptide, which is more hydrophobic in nature, they kind of like drives the overall aggregation process and has the most dominant residue contact in when they are like in the aggregate. So we can see that they probably dominate because of this. They want to be in one aggregate because of their hydrophobic nature. In addition to the hydrophobic nature, they also forms like H bonds. And as Alexis showed that you can also calculate the H bonds for from the GROMACS software. You can then plot or make them such H bond contact maps. And you can see that with the the residue H bond map. And you can again see that the tyrosine forms most of the H bonds with different other residues of the other peptide molecules. So overall, this hydrophobic nature of these different amino acid residues, mostly the tyrosine here, actually drives the actual aggregation behavior or actual aggregation pattern for these peptides which we made up here. So these are like some of the examples which you can do in addition to the inherent GROMACS analysis tools. You can use these Python tools to perform this kind of analysis and show the to understand the detailed nature of the simulations, what you have performed during this, what you can perform using MD simulations. So so this is it for my first part of the lecture. In the next part, I will show you one more example of this peptide aggregation study, which is like more into from our research and what we observed from that part. And then I will also talk about the coarse grain MD simulations and how you can use or what you should do in implementing these coarse grain MD simulations. Okay, so let's start again. And now mainly I will go through one of our study where we have actually studied the aggregation behavior of a bunch of structurally similar therapeutic decapeptides. And we used MD simulations, and also we used NMR simulation, NMR experiments in collaboration to validate our simulation results. And I performed this study with Paul Larson and Andreas Hugert from Fing Pharmaceuticals. So the main goal of this study was to investigate the aggregation behavior of structurally related therapeutic peptides, cetrorelix, ozorelix, and D-phenyl-GnRH, which are all analogous to gonadotropin-releasing hormone, GnRH, and which is a key peptide hormone in the human reproductive system. So cetrorelix and ozorelix are basically GnRH antagonists. So this can induce an immediate reduction of gonadotropin levels by inhibition of their secretion from the anterior pituitary gland. And D-phenyl-GnRH is basically an agonist. So initially they are designed to stimulate the secretion of gonadotropins, and a continuous application results in the decrease of this pituitary hormone secretion. And their potential application is for like prostate and breast cancer and endometriosis. And one of the cetrorelix based formulation is already approved for in endocrine therapy. So here are the structure of these 3 different peptides. And here are the amino acid residue list. And here you can see that a bunch of amino acid residues are basically not natural amino acid residues. For example, D-naphthylalanine and D-phenylalanine, and then there are some other residues as well which are not directly natural residues. So to perform simulations with this kind of peptides or therapeutic drugs where you have this kind of non-natural amino acids, you need to do some additional work rather than just using one of the force fields. And to do this, there are some described methodology or process you can follow. And we followed those processes, like we used a Swiss side chain methods, where there were like these different kinds of non-natural amino acids were parameterized for charm force fields, and we used them, and we use the charm force fields for our simulations. So to study their aggregation behavior, we perform a system or simulation box of side length of 15 nanometer cubic box, but side length is 15 nanometer, and the number of molecules or peptide molecules we placed initially randomly in the box is like 20, and this represents the concentration of about 10 millimolar. And to increase our statistics of the simulation results, we perform each simulation for each case like 3 times, and the total simulation time was 500 nanoseconds. And we perform for these 4 different simulation systems like cetrorelix, ozorelix, D-phenyl-GnRH with uncharged histidine. Note that I have already showed you the amino acid residues. Among them, histidine can be in charged and both in uncharged system based on the pH of the system. Histidine has a pK of like about 5.5. So like at about physiological pH, which is 7.5, it can change its charge state. So we used both the systems with uncharged histidine and charged histidine. So first, we can see the aggregation pathways of the system, and we can see that for cetrorelix, in the aggregation pathway graph, the maximum aggregation size which can become is like 20, and it can first become a dimer, and then the dimer can become a trimer, and then that's how it evolves into a 9 or 11 aggregate size, and then these two can merge and form a 20 aggregate size, and this is like the final aggregation structure in one of our simulation. On the other hand, when D-phenyl-GnRH, where the histidine were charged, you can see the maximum aggregate size you can see in the simulation is like about 8. And you can see a bunch of monomer become dimer, but then the dimers also dissociate into monomers. So the dimers or the higher aggregate sizes for these diphenyl GnRH are not quite stable compared to the cetrorelix peptides. We also perform these aggregation pathways or aggregation pathway analysis for both ozorelix and also diphenyl GnRH with uncharged histidine. The aggregation pathways for ozorelix and the final aggregation state is quite similar to cetrorelix, which has like also the similar structural characteristics in terms of the amino acid residues. And then we also have this structure diphenyl GnRH with uncharged histidine, which is kind of like in between the cetrorelix, ozorelix, and the diphenyl GnRH with charged histidine. So it forms quite large aggregates, but it does not conform all the molecules into one large aggregates. So the maximum aggregate size here was about 15. So once we have this understanding of their overall aggregation behavior, we then try to understand the aggregation kinetics. And one of the way to understand that was like the binding and unbinding events. Like whenever two peptide monomer become one dimer, we consider that as a binding event. And when one dimer dissociate into two monomers, we consider that one unbinding events. And we can see that for cetrorelix and ozorelix, we can only see these dynamic binding and unbinding events for the initial 50 to 100 nanoseconds. And then after that, there are like not much binding or unbinding events. And for uncharged histidine, we could see that binding or unbinding events up to like a certain time. But for the charged histidine, we can see it's like the binding and unbinding events is constant throughout the whole simulation time. So like what this binding and unbinding event tells us, I mean, based on this number of binding and unbinding events, we can consider or we can calculate the collision acceptance probability, which is the ratio between the difference between binding and unbinding events and divided by the number of binding events. And the higher the SCAP value or collision acceptance probability, it represents higher aggregation propensity. So a collision event close to, so a CAP value close to 1 will be an ultimate aggregate prone peptide, and the collision acceptance probability 0 will be no aggregation propensity, will represent no aggregation propensity. And here we can see that the higher aggregation propensity is for cetrorelix, then ozorelix, and then with uncharged histidine. And then when the diphenyl GnRH we used with charged histidine, that is like very low. And then we can see a similar pattern in the number of hydrogen bond per peptides. So it follows a similar structure, like the number of hydrogen bonds per peptides, like interpeptide hydrogen bonds, when two peptides are in aggregates and when they form hydrogen bond between them, interpeptide hydrogen bonds, they also follow a similar similar trend, like with cetrorelix being the highest and diphenyl GnRH with charged histidine being the lowest. While the number of H bond per peptide with the water molecules. So now this was like interpeptide H bonds, and these are like the peptides with the water molecules. So this shows an opposite trend, which actually makes sense because the more aggregation prone, the more it will do the hydrogen bonds or more it will be in contact with the other peptides. So it will form more peptide, more hydrogen bonds with the interpeptides. But if they are like in the monomeric form or separated between each other, the more it will have the opportunity to do the hydrogen bonding with the water molecules. So we can understanding the overall aggregation propensity for this using these analysis methods, and this also agrees well with our NMR experiments. With NMR experiments also showing that the cetrorelix is the highest aggregation propensity, and the diphenyl GnRH has almost no aggregation propensity. So now, as we discussed before, like with the contact map and everything, we can also try to understand due to what drives this aggregation propensity. And here we have performed this inter-residue contact interaction map. And you can see that here, like if you compare between these four different graphs, I mean, four different maps, that this initial peptide interaction is quite high in the both cetrorelix and ozorelix. While these three residues are not available in the diphenyl GnRH, they are quite different than these three. And for citrullinates and ozoralics, they are quite similar. And the absence of this actually makes this less aggregation prone compared to citrullinates and ozoralics. So overall, from this study, we summarize that the fraction unbound peptide and CAF values and also the hydrogen bonding showed a rank order of the aggregation propensity, which showed that citrullinates and ozoralics is quite similar, and the diphenyl GnRH with charge histidine is the lowest. And this rank order is quite similar to the critical aggregation concentration values and aggregation propensity given by the NMR and the other literature fluorescence data. And the aggregation transition network we derived from our simulations also shows that the aggregation pathways with citrullinates and ozoralics going into the higher aggregate sizes compared to diphenyl GnRH. And for citrullinates and ozoralics, the residues near the N-terminal, the first three residues near the N-terminal, play the dominant role into the overall intermolecular contacts, in contrast to diphenyl GnRH, which are not available in the diphenyl GnRH. And that seemed to be contributing the differentiating into the overall aggregation propensity among these peptides. So this is one of our example of how we can apply the all-atom molecular simulations into the analysis of the therapeutic peptides, in addition to the experimental results and what more information we can gain from simulation compared to the experimental results. For example, the NMR and fluorescence data in these cases were also giving us the understanding of how aggregate prone these peptides are, but not into the detailed molecular level information. We haven't really got much from those experiments here. So this is all about my lecture on this all-atom simulation methods. Now I will briefly go through the coarse grain simulation methods. And Alexei has already described a line or two about this coarse grain molecular dynamics method, but I will go into a bit more details. So basically what happens is, like in all-atom molecular simulations, you can see on this picture here on this left-hand side, there are like 4 water molecules, and each water molecules were represented by 3 interaction sites, 1 oxygen and 2 hydrogens. And in coarse grain, what happens is, like all these 4 water molecules, like 12 interaction sites, will be represented by only 1 interaction site. So 1 bead will actually represent 4 water atoms, but that's how it can actually gain the advantage in the saving the simulation time, and we can perform much higher or longer simulation time scales and length scales. And here's an example of a POPC lipid, or like a DPPC lipid, and you can see that all these atoms are represented by basically only 12 beads or 12 interaction sites in the coarse grain method, and this is how it is typically represented in the all-atom methods. But how actually this coarse graining is done? Like you are taking 4 heavy atoms or 4 heavy molecules and represented by 1 beads. Does it comes completely random, or there are like some procedures they follow? So mostly there are like different coarse graining approach, and one of the coarse grain approach we follow in our group is like the Martini coarse grain model. And in the Martini model, they have some specific approach to do the coarse graining, and basically there are like 4 different types of interaction sites they can define, which are like polar groups. So these are like for neutral group of atoms, so it represents the neutral group of atoms that would easily dissolve into water. And then there will be like a polar group of atoms, which will be represented by C beads, and this side represents group of atom which has hydrophobic in nature. And then there will be also non-polar, which are partly polar and partly non-polar, and charged beads, which contains mostly the charge. Now, this polar and apolar groups, P and C, this can be also subdivided into the degree of polarity, and it can be ranged from 0 to 5, with 0 is like not polar and 5 is the highest polarity. And this subdivision can be added, these numbers can be added by the side of these letters, like P. Bead can be also represented by like P0 to P5. So there are like now 6 different atom groups or bead groups. Then the nonpolar and charged type of interactions, like N and Q type interaction sites, can also be divided into 4 subtypes, like no hydrogen bonding capabilities that can be represented by 0 by the number. And then it can also be like A or D based on a hydrogen bond donor or acceptor, like D or A. And it can be both donor and acceptor and be represented by DA. So all these different kind of subdivision basically allow us to more accurate representation of the inherent chemical nature of the underlying atomic structure. And here is an example of this POPC molecule or DPPC molecule, which I showed earlier. So this is how it is actually now derived into 12 beads alone. So this first group here, which is a charged bead, so it should be Q, which is positively charged, it should be Q, and it choline group, and it represents like no hydrogen bonding options. So this is represented by a Q0 bead. And then the second group here, this one is phosphate, which is also a charged group. And this has also hydrogen bond acceptor probabilities. And this is represented by here, a QA bead. And then the ester groups, there are like 2 different ester groups here. So like this 2Na, this also has hydrogen bond acceptor capabilities. And then this whole aliphatic chain is represented by 4 different apolar interaction sites. So this represents the 15 methyl or methylate groups, which have like in 2 different chains we have. So that's how lipid molecule is basically coarse-grained, and this is the approach. All the molecules can be coarse-grained. So we used very frequently CGMD simulations in our studies or in our research, mostly because we could gain a lot into the time scale and the length scale. But one of the key issue whenever you perform CGMD simulation is like the use, or first you need to really validate your molecules first. So what happens is like in all-atom simulation, Alexia already mentioned that you need to go through a validation process. The simulation results actually means nothing. But for the CGMD, it's even more important to perform the validation first, because like it's even coarser than all atoms. So you have the probability of getting even more errors into the simulation because of this coarse graining the overall structure and overall chemical nature of the molecules. So in our different research, we wanted to use these different medium chain fatty acids like C10, caprylic, like caprylic acid, capric acids, and then myristic acids. So what we wanted to first use, before using these molecules into our coarse grain simulation, we wanted to really investigate how they behave in the coarse graining. So what we did is like we performed their aggregation behavior, and we tried to calculate their critical micelle concentration or CMC values, and compared with that with the existing experimental results and the experiments also we performed. So here is an example of this C10 basically. So this is how we have defined these 3 beads. So these are like the 2 chains, and this is like the head group beads, which is a Q bead. And then when we model these things or these beads such a way, we performed the aggregation analysis. What we have done is like we have performed aggregation at different concentration. So C10 molecules were placed in a box. This box size is like 25 nanometer in X and Y direction, and the length was about 50 nanometer. And we performed the simulation for 1 microsecond. And to perform this length scale and this time scale using all-atom method, this would have been take like a month. But within from this coarse grain simulation, 1 microsecond simulation for 1 case, it took only probably a day or 2. So this is a huge savings in terms of time or simulation time. So we perform this C10 aggregation behavior at different concentrations, and you can clearly see from these 4 different pictures that as the concentration increasing, the amount of free monomer is kind of decreasing, and the number and amount of aggregates also increasing. So what we have done is that we performed 5 different simulations at 5 different concentration, and we calculated the percentage of free molecules in each concentration, and we plotted it. And from this plot, we calculate the percentage of free molecules. What is the concentration where we get the percentage of free molecules at 50%? And in this case, the 50% will give us probably at about concentration of 15 millimolar. And this 15 millimolar is kind of like defined as the critical micelle concentration. So the critical micelle concentration is basically the concentration at which 50% of the molecule will become in aggregate form and 50% of the molecule will be in the free monomer state. So then we have performed a bunch of simulations for a bunch of systems for these 4 different molecules. So we try to mimic different pH condition, like at higher pH, all the molecule of this fatty acid molecule will be negatively charged, and at around pK about at near their pK value, 50% of the molecules will be negatively charged and 50% will be positively charged. And we also varied the ionic concentration, like ionic strength. We have studied without the ionic strength and we have studied with the ionic strength, and we have calculated the CMC value for all these different cases for these 4 different molecules. And then we have also performed some of the experiments, and we compare our experimental results. We compare our simulation results with the experimental results, and we observe that it agrees pretty well. But the difference is about 1.2 to about 2.5 times varies with the experimental results, with the experimental results being the higher value. So we assume that the CGMD results we have here, it kind of like underpredicts the little bit, but overall it trends shows that it can capture the aggregation behavior based on the ionic strength, based on the pH, based on the side length, the chain length of these fatty acids. So overall, we can consider that this coarse graining parameters which we developed here is quite reasonable to perform or to use in the coarse graining simulations. We also investigated or try to understand their aggregation morphology, like how much they can capture the morphology of the aggregates. And we also see that at higher pH, or when all the molecules are negatively charged, the micelle shapes and size are kind of like spherical. But as it increases, as the pH decreases or the uncharged fraction of the molecule increases and becomes 100%, all the molecules are basically forms kind of like a bilayer type of structure rather than spherical micelles. With higher simulation box, we also observe that they can form even vesicles. So this is what our validation, and with the experimental results in the literature, we also observe the same, that at higher pH, the fatty acid molecules mostly form spherical micelles, and with that lower pH, it forms kind of like vesicles. So overall, when we have this validation process, we have this validation with the experimental results, then we actually started using these molecules into our other coarse grain simulations, other complex systems, which contains like membranes and also the intestinal fluid molecules, in the presence of them, in the presence or absence of the intestinal molecules. So so overall, I don't really have any summary on this. So this is like, I think Alex has summarized well at the end of his presentations. So whenever we use the simulation results or the MD simulations, the simulation results actually can be represented in different ways. So we need to do a very good analysis of the results, and then we really need to validate each and every step of this simulation process. For the coarse grain, I think we can also do one additional step, like we can perform the simulation with coarse grain, and we can perform also the same simulation with all atom and compare them for some smaller systems to see how well the coarse graining parameterization is behaving compared to the all atom simulations.